us start by making a list of the possible external forces acting on an object that were discussed in the previous lecture. The gravitational force, the normal force, the friction force, the force of tension, the buoyancy, the applied force, and may I also add the force exerted by a spring that we will label Fs. The force due to a spring is similar to a tension force in that it exerts a pulling force when stretched, but a spring can also exert a pushing force when it is compressed. After you have identified the particular external forces exerted on an object, you add them up vectorially, and the result is called the net force. What is the use of the concept of the net force? Well, it is an integral part of 2 of 3 laws proposed by Sir Isaac Newton in 1687. Here is the first of these laws. An object that stays at rest or is moving at constant velocity is simply not accelerated. So the first law can also be expressed this way. If the net force on an object is 0, then the object has no acceleration. In an even more concise way, we can say that if and only if F net is 0, then A is also 0. Having no acceleration does not mean that there are no forces exerted on the object. It means that all the external forces have cancelled each other out. This expression of Newton's first law is avoiding the mention of the complication of defining inertial reference frame, which I am going to leave for a more advanced physics course. Consider the following situation. An object of mass m is attached to a spring which is itself attached to the ceiling in a location near sea level at the equator. The object is not moving. So, according to Newton's first law, the net force on this object is 0. 2 forces are acting on this object, the gravitational force and the force due to the spring. The sum of these 2 forces equals the net force, which is 0. It means that the magnitude of the gravitational force is equal to the magnitude of the force due to the spring. The nice thing about a spring is that its elongation is related to the value of the force it can exert, if you keep it in a proper range. Not too small, so that no change in length is noticeable, or not too large, so that the spring breaks or becomes permanently stretched. The change in length, delta L, from its relaxed length is proportional to the magnitude of the force it can exert. The symbol that looks like a fish is not an equal sign. It means that the 2 quantities are proportional. For example, if the change in length doubles from an earlier situation, it means that the magnitude of the gravitational force also doubles from what it was earlier. This does not quantify the forces yet, but it gives hints to their relationship with other quantities. Experimentally, when you increase the value of the mass m, the spring stretches more, and it does so in a proportional way, which means that Fg is proportional to m. Let us look at the effect of the distance between the mass m and the center of the Earth. If you transport your spring and mass at the top of a mountain, you would find that the spring is less stretched. The Earth is not a perfect sphere. The poles are closer to the center of the Earth than points at the equator. You would find that the spring stretches more at the North Pole. So the gravitational force decreases when the distance between the mass and the center of the Earth, labeled r, increases. Having a closer look at how the change in length in the spring decreases with an increase in distance between the objects shows that there is a faster decrease than a simple inverse proportionality. A better fit occurs when the relationship leads to the gravitational force being proportional to 1 over r squared. So far we have established that the gravitational force is proportional to the mass of the object and inversely proportional to the square of the distance between the center of the object and the center of the celestial body. This is as far as we've got. What if now we transport our entire apparatus to the surface of the moon? The mass m of the object is still the same, but the radius of the moon is smaller than the radius of the Earth. If we were to assume that m and r are the only quantities that affect the gravitational force exerted on an object, we would predict that the spring is more stretched on the moon, but experimentally we find that the spring is less stretched at the surface of the moon compared to what it was on Earth. So the gravitational force depends on more than m and r. When we change the Earth for the moon, we changed more than the distance r. We also changed the mass of the celestial body. How do we study experimentally the dependency of the gravitational force with the mass of the celestial body? It is not as if we can put the Earth or the moon on a scale. We will leave the problem of evaluating the mass of celestial bodies for later and find another way to decide on how the gravitational force might depend on the mass of the celestial body. Let us have a quick glimpse at Newton's third law before we spend more time working with it. It states that when two objects interact with each other, they exert a force on each other and that the forces are equal in magnitude and opposite in direction. The third law is not about the net force. It is about the nature of the interaction between objects. The interaction is never one-sided. The Earth is exerting a gravitational force of magnitude Fg on our object, but our object is also exerting a gravitational force of magnitude Fg on the Earth. Which means that from the point of view of the gravitational force exerted on the Earth, we have that Fg is proportional to the mass of the Earth. Combining all the relationships that we have discovered so far, we get that Fg is proportional to the product of the masses and inversely proportional to r squared. In fact, it is way more general than this. According to Newton, the gravitational force occurs between any pair of objects, so Fg is proportional to ma times mb divided by r squared. In this lecture, we have established relations of proportionality describing the effect of masses and distance on the gravitational force, but we still have not quantified the gravitational force, or any other forces for that matter. For this, we will need Newton's second law, which is the topic of the next installment.